Next we look into an example. Suppose we want to find the value for setting of this TMOD register. If we want to program this timer 0 in mode 2 and use 8051's crystal frequency as the clock source, and use the instructions to start and stop the timer. So, basically it is a software controlled timer that we want to operate, and we want to use this timer 0 in mode 2. Okay. So, definitely this TMOD setting. So, time for timer 1, these 4 most significant bits are for timer 1. So, they are all 0. Now, for these least significant 4 bits, so they are for timer 0, and out of that this gate bit is 0. So, this gate equal to 0, that is internal operation. Then this is your this count. So, that is for, then this second bit is C by T. So, C by T is 0, means we are looking for the timer operation. So, C by T is 0, and then 1 0. So, this is the mode identifier. So, this is the pattern that we have to load in the TMOD register if we want to do this operation. Okay. So, this is the summary of this timer modes. Okay. So, in mode 0, what happens is that, so this timer clock, so this comes from the internal source, and then this TLX has got 5 bits and THX has got 8 bits, and when it overflows, then this TFX bit will be set. So, there is a for timer 0. So, there is a TF0 bit, which is basically the overflow bit. So, when this timer overflows, this bit is set. In mode 1, so that was a 16 bit mode. So, again the same thing, TLX and THX. So, this is in mode 0, it was 13 bit, here it is a 16 bit timer, and again the rest of the thing is same. So, it will when it overflows, so it will affect the TF0 bit. Then in mode 2, so we have got this reload mechanism. So, this when this TLX is so it is an 8 bit count, it is an 8 bit timer. So, when the timer overflows, the TFX is set, and after that the value is reloaded from THX into TLX and the process restarts. So, this will be doing it periodically. In mode 3, we have got this two such timers, TL0 and TH0. So, there are 2 overflow flags, TF0 and TF1. Now, you see that this timer clock. So, when TL0 will overflow, so this TF0 will be set, and this when this TH0 overflows, then this is TF1 will be set. So, we will come to more detail with mode 3 later. So, we will see that later. Next interesting register that we have for this timer counter operation is the TCON register. So, TCON register, so this is the timer control register is TMOD. So, upper nibble is for timer counter, lower nibble is for interrupt. Okay. So, this is the timer control register or TCON. So, TMOD we have already seen. So, this is about the TCON register. So, this register you can divide it into 2 nibbles. Okay. So, this is the lower nibble. So, lower nibble we will not discuss now. So, they are for interrupts. Okay. For upper nibble is for the timer operation, and here you see those bits TR0 and TR1. So, TR0 is for running the timer counter 0, and TR1 is for running the timer counter 1. So, TR0, if you set this bit to 0, then the timer will be stopped, and if you set the TR bit to 1, then the timer will be started. So, previously we have seen that for soft controlled or software controlled timers, so we should program this TR0 and TR1 bits. So, those bits can be those bits can be set by using this by using some instruction that will affect this TR0 and TR1 bits. And this TF0 and TF1 also we have seen, that is basically the overflow. When the overflow occurs, then this TF0 and TF1 will be set. So, the TF the timer flag. So, here TF0 is for timer counter 0, TF1 is for timer counter 1. So, it is like carry. So, initially TF is equal to 0, and then when this THTL will roll over from all F to 0. So, if it is a 16 bit timer, then when it is rolls over from 65 FFFF hex to all 0, then the TF flag is set. So, TF equal to 0. So, we have not yet reached the final value, and Tf equal to 1 means we have reached the timer value. So, what we can do while generating a delay, so we can initialize those timer with some value, with some initial value, then start the timer by setting the corresponding TR bit, and now continually monitor whether this TF bit is set or not, because once the TF bit is set means that time has passed. Okay. So, we have that time value has been used. So, there are interrupts. So, we can do it in two ways. So, one is via this polling mechanism, another is via this interrupt mechanism. So, what I say is like this. So, if I have got this timer, now this timer when it overflows, so it will set that TF flag. So, what you can do, you can either poll this TF flag, so whether it is 0, whether it is 1 or not, and you can continually do that. So, you can initialize the timer and then start it and continually poll the TF bit whether it has become 1 or not. Other possibility is you can enable the timer interrupt. So, we will see how to enable the timer interrupt while discussing about the interrupts, but once if this is enabled, then whenever this TF is overflow, so this will generate an interrupt to the processor. So, the processor may be doing something else, and now it will be interrupted. So, it will go to the timer service routine. So, this is typically useful when you are suppose designing a digital watch. Okay. So, in the digital watch, so I have got this so hour part, then minute part and second part, fine. So, the basic the main program, it may be continually getting those hour, minute and second values from some memory location and displaying it, and side by side it needs to update the time. Okay. For updating the time, so every second the processor should update the time value. And how will it do it? So, it will start a timer for a value of 1 second, and whenever this timer overflows, the interrupt is enabled. So, you can have an ISR, interrupt service routine, for that purpose, and then what that interrupt service routine will do? It will be updating the corresponding memory location for this hour, minute, second, those bytes. And naturally, so this my display routine, since it is reading from that location, so it will be displaying the correct time value. So, this way we can use these timers for designing some real time clock. Okay. So, these TF flags are the TF bits are useful that way. So, next we will look into the instructions that are required for this timer operation. So, set B TR0. So, this is bit addressable, this TCON register is bit addressable. So, you can say like set B TR0 or set B TCON.4, okay, or you can say clear TR0. So, set B TR0 if you do, then timer 0 will start, and if you are doing this clear TR0, then the timer 0 will stop. Similarly, we can have this set B TF0. So, it will set this timer overflow flag to 0 and clear TF0. So, this set B TF0 is generally not required, but this clear TF0 is required, because whenever you are sampling this line. So, if there is an overflow, then this bit will be set by the system. So, in your ISR, so you may like to reset that bit first, otherwise it will be taken as another interrupt. Okay. So, that way this clear bit is necessary. Similarly, for timer 1, we have got this set B TR1 and clear TR1, and we have got this set B TF1 and clear TF1. So, those things, and these 4 bits IU and IT1, IE0, IT0. So, this will come when we go into the interrupts. So, next we look into the timer mode 1. So, timer mode 1 is it is a 16 bit timer, as we know. So, in our example, so we will consider only timer 0, and knowing fully well that the same thing will also be true for timer 1. So, this 16 bit timer, so it has got TH0 and TL0 register pair. So, TH0 TL0 pair will be incremented continually once this TR0 is set to 1. So, TR0 being set to 1, so they will be this value will be incremented continually, and it will stop when this TH0 TL0 pair will reach 0, or say this TR0 has been is cleared. Like in a program, after some time, so you can stop this timer by say clearing the TR0, though it has not overflown. So, you can stop it in between by clearing the TR0 bit, or otherwise this timer will continually update. So, it will be looking into the internal system clock. Okay. So, it will be updating itself, and then when it will be at the end of each machine cycle. So, it will be counting it up by 1, okay, because that is the driving of the internal clock. So, when it reaches the value FFFF hex, then it will roll over to 0000, and then the TF0 bit will be raised. Okay. So, that is the mode 1 operation of this timer, and programmer can check TF0 and stop the timer 0. So, now it has, now the programmer as I said that it may be a polling. So, programmer in a polling mode can continually check for this TF0 bit. So, I can have an instruction like this, that jump, sorry, I can have an instruction like after setting the timer, starting the timer. So, somewhere I have got this set B TR0. Okay. So, timer has started, and after some time, so I can if I just want to have a delay. So, we can say that jump on not bit TF0 L1, where L1 is this place itself. So, this is the polling code. So, I am checking the bit TF0, and if it is not yet set, so I am just looping at this point. So, this way, so whenever this bit will be set, so it will be coming to the this check will be false. So, it will be coming to the next position. This way we can have this type of polling implemented in our code. Next, so how to use this mode 1? Okay. So, first we have to choose mode 1 for timer 0, and for that matter, so we set the control word for in the TMOD register to be 01 hex. So, 01 hex means the first 4 bits will be 0, first 4 bits will be 0, and the next 4 bits will be 0001. So, this part is for timer 1. So, that is not our concern now, and this part is for timer 0. Out of that, this is the gate. So, that means I am driving from internal source, the clock is internal source. So, this 0 will mean that it is a timer operation, and then these 2 bits. So, they will identify that I am operating in mode 1, that is 16-bit timer mode. The next important thing is to load this TH0 TL0 pair. Okay. So, this pair I am loading as FFFC. So, the count value that I have loaded is FFFC, and it is better that we clear this TF0 bit. Okay. So, for the safety, because previously maybe this TF0 was set and it was not cleared before this timer had started. So, it is to be on the safe side, we should clear the TF0 bit. So, we clear the TF0 bit here, and then we start set bit TR0. So, set bit TR0. So, it will start the timer now. So, from FFFC, so it will go to FFFD, okay, then FFFE. So, it will go like that. So, when it comes to 0, then there is an overflow. So, that will be detected. So, this is the thing. So, 8051 will start counting like this. So, it will be FFFC, FFFD, FFFE, then FFFF, then this 00. So, when it goes to this one, so this FFFF to 0000 at that point. So, if you monitor this TF1 bit will be set to 1. So, previously this TFG bit was 0. Okay. This is all TF0 bit. Okay. So, this is not 0 is not explicitly mentioned here. So, this is the TF0 bit. So, that is set to 0, and when this overflow occurs, then it will be coming. So, we can monitor this situation whether this TF0 is becoming 1 or not, and when this TF0 becomes 1, so we should stop the timer. So, we can stop this TR0, can reset this TR0 bit accordingly. So, when this TH0 TL0 rolls over from FFFF to 0000, the 8051 will set TF0 bit to 1. So, now this we can do it as I was telling, that we can have a monitoring like this, that jump on not bit this TF0 again. Okay. So, we can have something like that. So, that will mean that we are monitoring the TF0 bit, and as long as it is 0, so it will be looping here. Then we clear the TR0 bit to stop the timer operation, and then we clear the TF flag to so that next time when you want to operate the timer, so it should not create any problem. So, this way we can use this timer 16-bit timer in mode 1. So, the operation is like this, the crystal frequency. So, that is divided by this 12. Okay. So, this is in C by T equal to 0. So, this 12 cycles in case of 8051, 12 clock cycles constitute one machine cycle, and this timer value is updated per machine cycle. Okay. So, that is why, so it is internally it is divided by 12. So, this division is internal. So, it is internally divided by 12. So, this type of clock is generated, and then this it is fed to an AND gate. So, this is all logical. Okay. So, whether it how is it physically implemented, so that is not known, but logically you can think about it as if this TR bit is ANDed with the clock, and when this TR bit is 1, then only this clock will be allowed to reach this timer value, and this timer value will start up counting. So, from from whatever be the value, so it will go on up increasing, and then when it rolls over from FFFF to 0, then this timer overflow flag FTF will be set. So, how to calculate the delay? Okay. So, it depends on the crystal frequency, of course, but how can we do this? For example, suppose the value that I have initialized with this TH and TL register pair is YYXX hex. Okay. So, if it is YYXX hex, you know that if so how many cycles will it take to go to FFFF? So, it is FFFF minus YYXX plus 1. So, after so many cycles the overflow will occur, and if this is 11.0592 is the crystal frequency, so that turns out to be 1.085 microsecond. Okay. So, that way I can say that it is so this has to be, so this is divided by 12 first of all. So, if you look into this previous slide, so this crystal oscillator is divided by 12, and that is fed as clock here. So, here also, so this divided by 12, and then if you convert it into time, so 1 by f, so that turns out to be 1.085 microsecond, or in decimal you can just the same thing. So, instead of taking FFFFF plus 1, so you can say simply write like 65536 minus this YYXX in decimal maybe say NNNNN. So, this is multiplied by 1.085 microsecond. So, this way given this time value, the timer initial value, so we can calculate what is the actual delay that is produced. Suppose we want to design a square wave with 50% duty cycle on port bit 1.5. So, we have seen previously this example, but there we were using that soft delays. Now, here we will be using this timer delays. So, we are using this timer 0 mode 1 16-bit. Okay. Then move TL0 0F to hex. So, and this TH0 0FFX. So, this timer value that is loaded is FFFF F2. Okay. So, this is the value that is loaded. Now, we complement P 1.5. So, that way we whatever be the previous value of this port, so that gets complemented. Then we give a call delay. So, the delay routine is called. So, we will see that delay routine, and then SJMP here. So, it will come back to this point. So, again this timer will be loaded and the value will be complemented. So, the delay routine is like this. So, we set bit this TR0, this timer is started. Okay. So, previously the delay routine was doing some register decrementing, jump not 0, etc. So, here instead of that we are starting the timer, and we are now monitoring the TF0 bit. So, this JNB TF0 again. So, this will be continually looping here till this TF0 bit is set to 1. So, when this TF0 is set to 1, at that time this this delay has been seen. So, it is clear TR0 and clear TF0. So, it will stop the timer 0 and it will clear the timer 0 flag and it will return. So, this program it will be doing that thing like say it will be doing this operation. So, after that again, so after this, after we have returned from this delay routine, so it is basically this jumping to this point here, and here again we are initializing the timer to TL0 and TH0, those two registers we are initializing to values. So, this value is same for both time high and time low. So, you get this value as the as a 50% duty cycle. So, you can also very easily calculate what is the delay that is produced, because the count value that you have is the initial value is FFF2. So, using the previous formula that we have got here, so you can calculate what is the on time and off time. Okay. So, accordingly you can say that okay, so much of what will be the frequency of this square wave that is generated. So, that can be calculated very easily. Next, so we try to find the frequency. So, this program, so this is generating a square wave on P 1.5 using timer 1, okay, and we want to find the frequency. Now, so first of all this T mod setting. So, T mod setting for, so second nibble is 0, because the previous example was using timer 0. So, this is using timer 1. So, timer 1 means this this lower order bit, lower order 4 bits of this T mod register. So, they are all 0, and here I am setting as 1. So, it is 0 0 0 1. So, these two bits tell that I am using this timer 1 in mode 1. Then we are initializing this timer with the value 3476 hex. Okay. So, for that purpose TL1 is loaded with 34 and TH1 is loaded with 76. I think there is a problem here. I think this is like say this TL0. So, it is actually having the lower order byte. So, that way, so this one is slightly wrong. So, this should be TH1, it is not if you want to get this 3476 here. So, this is not 3476, sorry. So, this is not 3476. So, this is 7634, because this TH register has got 76 and this TL register has got 34. So, it is 7634. So, we are initializing this TH TL pair, then set bit TR1. So, we are starting the timer 1 at this point, and then jump on not bit TF1 back. So, this is basically that polling of that line TF1. Then we are clearing TR1. So, TR1, so this timer is stopped. Then we are complementing the bit. Then we are clearing the TF1 bit. So, TF1 bit is cleared. So, this timer is now that previously whatever this TF1 was set. So, that is cleared at this point, and then SJMP again. So, it goes here and again the timer is loaded. So, this is again 50% duty cycle case, but the value that we have loaded is 7634 hex. So, question is to find the frequency, and it just has to simplify the problem, we do not include the delays of these individual instructions. So, to get a more accurate thing, like you have to take into account this individual instruction delays also, but they may not be very high compared to the delay that is produced by the timer. So, they can be neglected for our discussion. So, what is that? So, we have loaded this initial value as 7634. So, our total clock count is FFFF minus 7634 plus 1. So, that is 89 CC, so 35276 clock count. So, this half period, so this is so since this delay is used for both on part and off part. So, we can say that for each of the parts, so delay is 38.274 millisecond. The whole delay is the whole time period of the signal is 2 into 38.274 millisecond, that is 76.548 millisecond. So, frequency of the square wave that is generated is 1 upon 76.548 millisecond, it is 13.064 hertz. So, mode 1 is so this is not auto reload. So, we need to reload this TH1 and TL1 registers separately, and then only we can this TH1 and TL1 registers, every time you need to restart the counter, restart the timer, you have to reload this TH1 and TL1 pair. The same is true for this timer 0. However, if we are looking for this auto reload mode, so we have to use the mode 2. So, in that case, many times this reloading here, as we have done in this case. So, every time after producing something, again we are loading this value. So, that will not be required. Okay. So, we will see that in mode 2 discussion.